Usually it's still loading in my streaming service. Are we here? Am I signed in right now? Okay. All right. So I'm going to assume that we're live. Uh, Now I want to finally just welcome everyone. I'm very glad we are all here finally, and it's been a long time coming. And now, through some experimentation, we're going to be streaming our first math talk of the year for the Math and Stats Student Society at U of S. Online on stream, not through a video conference service. And I'm very excited about that. Beside me is the picture of my esteemed speaker, Christopher Mahadeo. I'll introduce him. He is a fourth-year PhD student under Dr. Stephen Ryan. He is working, what's a topological recursion relation to Higgs bundles? That's his topic or topic of interest. His topic today is making donuts from scratch. He's going to be talking a little bit about Morse theory, as you can see below me right now. He also has a grant, I guess, or a teacher scholar doctoral fellowship to teach linear algebra next semester. So I believe he's excited about that, and this will be a bit of a trial run for how he's going to be teaching. But during the talk, there is our Discord link down below. If you have any questions at any time during the talk, you can join the link and you can join our voice chat question queue. And whenever we're ready to answer your question, we will be joining you into the session to answer a question directly, because I can't really understand maybe what you want to ask in chat. So it'd be better if you come and speak for yourself. But now, without further ado, let's get to the math. So I'll hand it over to Christopher, and we can take it away.
Hello. I hope I am being heard by everyone. I also hope that now, as I look at the stream and see slight delays between things, that somehow my voice and what you will eventually see on the paper somewhat overlap. I'm taking a moment just to see how that is lining up. There's a chance it's a little bit laggy, so there's a chance that you might hear me saying words and they will then appear on the screen, but I think that is just the life we have to live right now. So, okay, I will begin the talk. So, in these trying times, many people have taken to baking breads to help the days go by. I'm not here to talk about breads, I'm here to talk about making donuts. I want to just start with the references that I used for this, get that out of the way right away, is Morse Theory by Milner and An Invitation to Morse Theory by Niculescu, both very good books. Milner, a bit more of a classic. A quick overview of what's going to happen in this talk. I'm going to introduce some various tools and ideas. Some you may have seen before, critical points, etc. Some maybe are new to you. What's a Morse function? What's a homotopy? I understand that there's somewhat of a variety in the audience, so hopefully everyone gets something out of that. I'll state a couple of theorems, in particular the Morse lemma and the so-called fundamental theorems. And most importantly, I'm going to draw a lot of pictures. The kind of outline as a whole for this is, well, I'm talking about making donuts. So I'm going to tell you the ingredients. I'm going to tell you the recipe, and then we're going to make some donuts. A quick last thing before I get to actually writing stuff down is, casually veiled in the witty humor that is the title. This is a talk on Morse theory. And just the main idea of such is that we want to understand the topology, or the shape, of a manifold. I'm always going to call it dimension n. And if you have no clue what a manifold is, just think about a donut by studying functions on that manifold, or donut. To give a maybe a more down-to-earth motivation for this, I want to appeal to something that we've probably all seen before. So let me ask you a question. Given some function f from R to R, our usual first-year calculus type question, or function, how do we sketch F? Right? Lord knows this is a whole section in the curriculum of handling curve sketching, and we should recall that the answer pretty much boils down to finding and classifying critical points. A little bit more pictorially, if I told you where I had critical points and I knew a little bit about them, I can somehow piece the function together, and I know what's going on. Now, this is not exactly what is going to happen in this situation, but this is the sort of idea that I want you to keep in mind. We're going to do this, but in a much, much more abstract sense. So let's get into it. With the first part of our cooking adventure are the ingredients. So what goes into making a donut? Well, unfortunately, I need to drop a bunch of definitions on you, just so that we can handle what's going to come. So definition, let f be a function from M to R that is smooth. A point P inside of that manifold M is a critical point if the induced push forward on tangent spaces is just the zero map. Now, if we're not entirely sure what I mean by that, if I have local coordinates, so I have some local coordinates, call them x1 up to xn around my point P, then this is equivalent to asking that all of the partial derivatives are equal to 0. Oops, that was a... That is to say, my gradient vector is 0. At this point, again, I'm not entirely sure how things are going to be matching up my voice versus the stream, as I can see a bit of delay in the stream, so I apologize for that. But we're just gonna hope for the best. So that is a critical point. So we'll call a critical point non-degenerate. If the matrix of partial second derivatives, also known as, at least in coordinates, a matrix representation of the Hessian, is non-singular. And by non-singular, of course, in the terms of a matrix, I just mean that the determinant is non-zero. The last piece of this is the index of my function at this critical point. This is the number of negative eigenvalues of the Hessian. So this has just been a bunch of words. Maybe we were super down with what I just said and we're feeling it. If we're not, let's draw some pictures and try to understand what I mean, in particular by non-degenerate and index. As I trust we're all somewhat cool with the notion of critical point. So let's see some examples. Well, when you're doing examples, you always start small and easy. So let's think about a very simple function. F of x is equal to x squared. That looks something like this. And well, I know that I have a critical point at the origin right here. What is its index? Oh, if I look at the Hessian, in this case, just the second derivative, this is 2. So there are no negative eigenvalues. So in this case, I have index 0. Another simple example, let's take this function that I have here and just flip it around. And let's pretend that that's touching right there, because drawing is hard. What about the function f of x is equal to negative x squared? Well, again, I know there's a critical point at the origin. If I look at the Hessian in this case, just the second derivative of negative 2. So I have one negative eigenvalue. So this will be index 1. One kind of observation that I want to make that will be useful as we go forward is the shape here and how it relates to positive and negative eigenvalues. So here, in this first example of x squared, I have only positive eigenvalues, and I have this critical point. So the kind of picture that I want us to have in mind is around that critical point, things are flowing towards it. So I have one dimension of flowing towards the critical point. That is how I'm going to picture a positive eigenvalue. A negative eigenvalue, I want to think that things are flowing away from it. That was an atrocious arrow, I apologize. Let me draw that again. And so I want to think about these negative directions as flowing away. So again, positive, keep in your mind something that looks like x squared. It all flows down to the bottom. Negative eigenvalues, I want you to think of negative x squared. You put a little drop of water on the top and it flows down the sides. Okay, well in particular, these were functions with nice non-degenerate critical points. What about some with degenerate critical points? What do those look like? Well, a simple example of a degenerate critical point is something like the function f of x is equal to x cubed, where again we have to understand that drawing is hard. If you check this, taking the second derivative, you can see that it does not satisfy the Hessian being non-singular. In particular, at the origin, the second derivative is 0. So this is an example of a non-degenerate critical point. But okay, right? These are just curves and lines. Those are easy. You know, we want to deal with more complicated things. So let's bump up the dimension a little bit. What about examples in dimension 2? Okay, well, let's still try to live in, or I guess, examples of surfaces. Well, let's still try to live in easy life. So I'm living in 3 dimensions here. Let's think about the function f of x, y is equal to 1 minus x squared minus y squared, all square rooted. Well, this is the top of a ball, the top of a hollow spherical shell. And I definitely have a critical point at the top. And you know, let's try to apply our thinking about flowing away or flowing towards critical points. if I'm at the top here, it looks like I have two dimensions of flowing away. I can flow kind of parallel to the page, or I can flow kind of perpendicular to the page. And I have two dimensions that I can flow away. That means I have two negative eigenvalues. So this has index 2. And this is an example of a non-degenerate. In more dimensions, what might a degenerate one look like? Well, how about something like the function f of xy is equal to x squared? This, for every choice of y, I have a parabola. So I have a shape that kind of looks like, again, drawing is so hard, a shape that kind of looks like this. And here we might ask, well, where are the critical points? Well, what I have is a line of critical points along the bottom. And kind of just thinking immediately about this, there's one nice direction of flowing, which would be flowing down the half pipe, but there's not this second direction. You can definitely check and verify that the Hessian is singular in this situation. So, okay, we've looked at a couple of examples of non-degenerate critical points, and what we've seen is that they can tell us a little bit about how the graphs kind of flow around those critical points. But okay, that was fine and dandy for functions. How can we apply this to a manifold? Well, this is going to be the first of our theorems, the Morse lemma. What does the Morse lemma say? Well, if P is a non-degenerate critical point of some function f going from my manifold to R that has index lambda, well, then what I can do is I can choose local coordinates around this point P such that two things happen. Firstly, these coordinates are chosen such that P is the origin. And maybe importantly, my function looks like a constant minus a bunch of quadratic terms, lambda of them, in fact. Added to that, I have a bunch of quadratic terms, n minus lambda of them. Whoops. So what this is saying is that I know how a function, that given a function on a manifold, around non-degenerate critical points, I know how things look. In, kind of half-assedly in a picture, if I have some kind of manifold, what's up, at some point P where I have a critical point, I have lambda dimensions of directions flowing downwards, and n minus lambda dimensions flowing inward. So n minus 1 flowing towards the critical point, n minus lambda flowing towards the critical point, lambda flowing away. So this gives me some sense of what's happening in that area. And so that's great and all. That's for non-degenerate critical points of functions. If all of the critical points of my functions were non-degenerate, then that might tell me a lot about my manifold, because then instead of just knowing the information around these special critical points, every critical point would be non-degenerate, and I would know how it looks around all those points. And so this leads us to another definition. A Morse function this is a smooth function having only non-degenerate critical points. So, okay, what are some examples of Morse functions? Well, let's start simple. I started with just curves and stuff before, so let's start with some nice curves and stuff. Well, I had these nice examples before. F of x is equal to x squared, f of x is equal to negative x squared. And those were nice functions with good non-degenerate critical points. But, those were less functions on the curve itself and more so a function from R to R. But can I recast that as a function on the curve? Absolutely. Given this curve, I want to consider the function f of x, y is equal to y. And in this case, of course, y is equal to x squared. But this is a wonderful function from my curve to R. And I said before that this has its critical point at the origin, and I have my points, everything is flowing towards that point. Okay, what about my other example? I could do the same thing. In this case, I can still say f of x, y is equal to y. And this is a nice function that one critical point is non-degenerate, and I have exactly the picture that I had before. Before, I was thinking about maybe just functions. That was just casually a function from R to R. But this is now a function from a curve to R. So I'm really stepping it up a little bit. And one idea that I want to take from this is the notion of a height function. Right? In this case, the variable x was enough to describe what was going on here. I was only looking at the projection of this onto the y-axis. Is this something that I can keep doing and a game that I can keep playing? Well, let's, for sufficiently nicely drawn images, it should be clear. Suppose I had this curve, which drawing is hard, and I think about its projection onto the y-axis. Looking at this, I'm thinking about, well, critical points would be places where the tangent is horizontal. So maybe something like here, 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 and here. Right? This point, this point, this point, and this point. And if I want to know about the index, I can try to think about what I thought about before. I can try to think about these two examples above. At this very bottom critical point, it looks like things are flowing towards. I have one dimension of flowing towards, no dimensions of flowing away. That's going to be index 0. This critical point above it, same kind of thing, right? It looks like I have one dimension flowing towards, none away. So that's also 0. Let's go to the critical point on the right. It looks like I have two directions where I flow away, so I have one dimension of flowing away. That's one negative eigenvalue. Whoops. I might have said critical point before. I, of course, meant to say directions flowing towards means no negative eigenvalues. So this is one negative eigenvalue. And similarly up here, it looks like I have one negative eigenvalue. And so in this sense, the height function, pretty nice, as we can try to extrapolate information of our indices, the index of critical points, by at least looking at these shapes. But alas, this is just the simple life. Chris, these are just one-dimensional things. Life is easy in one dimension. How does this break down in more dimensions? Well, I'm going to slap a couple of examples down for you. So we're in 3 dimensions now. Let's look at the following shapes. A sphere. A weird piece of ginger that you bought at the store. And the only true thing in life, donuts. And I'm going to think about, in each case, their projection onto the z-axis. Again, I can identify critical points very quickly. On the sphere, I have one at the bottom, one at the top. On my weird funky thing, I have one at the bottom, one in this middle area, and one at each peak. My donut maybe is a little bit less intuitive. I have one at the top, one at the bottom, and one at the top and bottom of the donut hole itself. So again, let's take a look and see if we can figure out the indices of these critical points. Let's look at the sphere first. Well, at the bottom, it looks like I have 2 dimensions of flowing towards this critical point. I can flow parallel to the page, and I can try to flow like perpendicular to the page. So that's 2 positive eigenvalues, no negative eigenvalues. That is 0. At the top, I can flow away in 1 dimension. That is parallel, and 1 dimension that is perpendicular. This is 2 negative eigenvalues, so dimension is 2. My amorphous shape, at the bottom, I have 2 directions, 2 dimensions flowing inwards. So index 0. At both peaks, it looks like I have 2 dimensions of flowing downwards, parallel and perpendicular, in both cases. The parallel one and this kind of perpendicular shape. Again, drawing in 3 dimensions is hard, so hard. Each of these look like index 2. Again, as I have 2 dimensions of flowing down, so 2 negative eigenvalues. What's different now than we had before is this interior one. It looks like in the parallel, I have 2 pieces flowing towards it. Sorry. I have 2 directions where I'm flowing towards. So I have this 1 dimension of flowing towards. But then it looks like I have 1 dimension of flowing away. And so in this case, I have 1 dimension of positive eigenvalues and 1 flowing away. So this will be index 1. I hope we're cool with that. Again, I'm trying to use a bit of the intuition of flowing towards or away from critical points. So we're going to do this again for the torus, and I'll say that we're doing this for a particular reason for the torus and the sphere. The torus at the bottom looks like I have 2 dimensions of flowing towards, parallel to the page and perpendicular to the page. Nothing is flowing away, so that's index 0. At the top, I'm flowing away in the parallel direction, flowing away in the perpendicular direction. 2 downward flows, index 2. These 2 donut hole critical points now, they're a bit of a question. What's happening? Well, the top one, if I flow along the inside of this donut hole, I flow down. I flow away from the point. But if I look upwards, it kind of looks like I flow into it from above. So that looks like 1 negative eigenvalue, index is 1. Similarly, for this one down here, along the donut hole, it looks like I'm flowing inwards. I'm going to maybe zoom in this a little bit. For this instance, whoop. Here, I'm flowing inwards along the donut hole and away kind of along the other direction. And, in some sense, looking at this donut picture in particular, things kind of match together nicely, or how the flows work. But in particular, this is also index 1. So again, just the quick recap, as this is going to be important for us, we got the 0 at the bottom because there were 2 dimensions of flowing towards the critical point, parallel and perpendicular. 2 at the top, there were 2 dimensions flowing away, one parallel to the page, one perpendicular to the page. And each of the donut holes had one flowing towards and one flowing away. Cool. So I was a bit fast and loose here. I talked about height functions. We drew some pictures. All was lovely. Are height functions always Morse functions? That's a perfectly reasonable question to ask. And the answer to that is no. If I take my donut and I flip it onto its side the way any normal person has a donut sitting on a plate, I have a circle of critical points at the top. And none of these are non-degenerate critical points. It is in fact a circle of degenerate critical points. So these are all bad. And this should lead us to a natural question of, okay, well, what the heck? Sometimes there are Morse functions, sometimes there are not. So we should be asking ourselves, can we always find a Morse function? And I'm not going to go super into this at all, but the answer is yes. And in fact, they are very common. I guess I should put the words that they are. That is to say, they are generic. So, okay. I just spent a lot of time talking and drawing pictures. I want to recap what we just did. So I threw around a bunch of definitions for you. But the important thing that we should take from this part of the talk is that around non-degenerate critical points, by the Morse lemma, I know how things look, a la these pictures of the circle, the sphere, the ginger, and the donut. So what this means is that I know what the ingredients are. The ingredients are Morse functions. In particular, I want the information of a non-degenerate critical point with index. This will be the ingredients to our donuts. I live in this soft concern that maybe questions were being asked and they were not being relayed. So I've not heard anything, and I'm going to keep continuing as I'm looking up the time. So I told you the ingredients, but what about the recipe? Well, it doesn't help me to give you ingredients without telling you how to put them together to make a donut. So we need a couple of definitions for this. So some definitions. Let f be a function from your manifold to R. I'm going to define M upper A. This is going to be the preimage of negative infinity to a. In other words, these are all the points in the manifold such that f of p is equal to or less than a. As a quick picture, what do I mean? If I give you our lovely function given by the quadratic, and I think about this line being y equals 1, this green part is m1. That's everything beneath value 1. If I think about a sphere, and I project this onto the, let's say, the z-axis, and I think about this point here, a, well, this whole part down here, this is MA. So these are our sub-level sets. It's the level set and everything beneath it. Okay. A homotopy is a family of maps f sub t going from x to y with t inside the interval 0, 1, such that there's a bigger map, big F, going from x cross 0, 1 to y, defined by taking a pair xt to ft at x, is continuous. I feel like in a similar spirit to me defining the critical points and such above, this maybe isn't the best way to think about it. I just want you to have in mind that, you know, x can be continuously deformed into y. And I will say, if there is a homotopy, that x is homotopic. That will be denoted by squiggly with one straight line underneath. Pictures, they are worth so many words. So what does a homotopy look like? Well, if I gave you two lines or two curves like this, you know, a homotopy would be something like a collection of curves that go from one to the other. So it might be a set of curves like this. That is to say, you know, you're slowly kind of passing from one set of curves to the other, and this can clearly be done in a way that just does not break or tear anything. A super classic example is that a torus is homotopic to a coffee mug. And if we just want to see this very quickly, you know, if this were all made of clay, I could take the bottom of the coffee mug, move it upwards, and then I would fill in this, and I would have a very useless coffee mug that's solid. And I could then squish everything so that it's back inside of the shape of a donut. So homotopy, I want you to think in your head, you have Play-Doh, you can squish it, you can pull it, but you cannot rip it. The last definition that I need before I tell you the recipe is of an n cell. So an n cell, well, that's just an n-dimensional open ball. So a 0 cell is a point, a one cell is an open interval, two cell is an open disk, etc., etc. Okay, so sub-level sets, homotopies, n cells. Let's get to the recipes. The recipes in this case are what are called the fundamental theorems. And there are two of such theorems. They will tell us how to use Morse theory to build shapes. So, theorem number one. Let f be a function from m to r smooth. A is a number less than b. If the preimage of the set AB is compact and contains no critical points, then the sub-level sets MA is diffeomorphic to the sub-level set MB. Furthermore, they are homotopic. Or I can write this in a better way. Furthermore, MA homotopic to MB. So what is this saying? I've said a bunch of words here, but the important thing is not what is written, it's what does it mean? What the first fundamental theorem is telling me is that if I have sub-level set, and I look at another sub-level set that's higher up than it, and in the sense that B is bigger than A, as long as I've not crossed a critical point, they look the same. To give a small sketch of like what that could possibly mean, it's something like if this was MA, well, that is kind of like homotopic to, let's say, MB. That looks like this. Where inside of this, I can actually find my MA, and I can get to it just by sliding my function, by just sliding my manifold downwards. Now, I'll stop here for a hot second and say I did not prove anything up until this point because I wanted this to be more about the pictures of what's going on, but I'll say this idea is how this is proved. It's flowing along gradient lines. But for now, the only important thing about theorem one is that if I don't pass a critical point, they look the same. That's great. So if I know how I look at one point, I know how I look until I hit a critical point. But what happens when I hit a critical point? That's now the elephant in the room. But that is addressed in the second theorem, theorem 2. Theorem 2, so I have a function f going from m to r, smooth. T is a non-degenerate critical point. Of index lambda. And I'll say that just f at p is equal to some number c. So if the preimage of a little ball around C is compact, and the only critical point init is P. Then we have the following. The level set just above my critical point is homotopic to my level set just below the critical point with a lambda cell attached. I'm going to put attached in quotation marks here because I'm not going to tell you exactly how it's attached. But so what does this mean to try to draw a picture mirroring what I had above? Well, what this is saying is if I have some level set, some sub-level set here, m c minus epsilon. So I definitely forgot to write this, but of course epsilon is just some number, some small number bigger than 0. This will be homotopic to something that looks just like it, but somehow I have attached to it a lambda cell. I have attached some kind of handle to it. So I'm going to take a quick moment just to emphasize what we have here. If you do not pass a critical point, your sub-level sets effectively look the same. You can continuously deform it as though it was a piece of Play-Doh to the other. When you pass a critical point, you're adding some kind of handle. Something non-trivial is being done to your shape. Okay. So our kind of conclusion here is that the recipe are the fundamental theorems. As I just told you that, as kind of we can see that they will tell me how to build something. What was the input? The input was a non-degenerate critical point together with its index. So I promised that we would make donuts today, so let's make some donuts. Let us make some donuts. What donuts do we want to make first? Well, we're in Canada, we have Tims, there's only one place to start. Let's make a Timbit. So if I want to make a Timbits, this is effectively trying to construct a sphere. I'm going to cheat a little bit and show us what the sphere looks like, because I just want us to recall what we saw before, which was what are the indices. We saw the index at the bottom was 0, the index at the top was 2. And I just need some labels. So I'm going to say that the top corresponds to a point Q, the bottom to a point P. I want to apply my recipe. Let's see what happens. When A is less than P, I'm somewhere doodling down there. That sub-level set is the empty set. Okay. What happens when I pass P? So, I'll say that I'm a little bit bigger than P. Well, MA should be homotopic to the empty set. I'm going to write a plus here because, again, I was a bit fast and loose with what attaching means. That's the empty set plus a 0 cell. The empty set, that's just the empty set, and the 0 cell is a point. And it happens that a point is homotopic to a disk. How does that come to light? Well, I have a disk. I can push everything towards the center. And so what I have is a point. So what I'm saying now is once I'm a little bit above P, I have a disk which effectively looks like this kind of shape. Let's underline Timbit, because why not? Okay, as I move up and up, nothing changes. Everything will be homotopic. So as I keep going up, I'm going to fill this in more and more and more, and I'm going to eventually have like a weird Timbit with a byte taken out of it. Of course, I'm going to have a soft caveat as I am making sad, hollow Timbits with no interior. But once I hit that critical point, what happens? Well, what happens when A is a little bit bigger than Q? Well, my sublevel set should look like a disk. Sorry, let's be a little bit more proper. My sublevel set should be a little bit less than Q plus a 2 cell. When I'm a little bit less than Q, I look like a disk, and I said a 2 cell was a disk. So what I'm doing to this picture, sorry about that. What I'm doing to this picture is taking my sphere with a no top and attaching a top to it. And so like that, I have built a Timbit from just the information of critical points and indices. I see that my time is short, but I really do want to build a normal donut, and it will not take too long. So I hope we're cool with me building a normal donut.
I think that's fine. I think everyone's quite spellbound right now. We haven't had too much activity in chat. I think everyone's just watching. So go ahead, do it.
Okay. This will not take too long for people who have places to go and children to feed. In fact, now you know how to feed them donuts. A donut, in this case, I of course mean a torus. I'm going to cheat and draw the shape for us quickly. I need some labels. Remember, we saw I had index 2 at the top, 1, 1, and 0. I'm going to call these critical points in order P, Q, R, and S. And I'm going to play the same game here. What happens when A is less than P? Well, I'm doodling down here in the bottom. So my level set is nothing. It's the empty set. When A is just a little bit bigger than P, well, MA will look like a little bit less than P plus 0 cell. A little bit less than P, well, that's the empty set. And the 0 cell is just a point. So just like the example above, I have a disk. Okay, well, let's keep flowing. I keep flowing. I have disks. What happens when I hit Q? When A is a little bit bigger than Q? MA will look like M a little bit less than Q plus, in this case, a 1 cell. Well, this is a disk plus an open interval. And again, I was fast and loose with how things attach. So what I will say to you is that this is homotopic to a cylinder. And I will draw a picture quickly. As for what I mean, I start with my disk. That was not a nice picture. I'll start with my disk, and I'm going to add to it a handle. Then what I'm going to do is thicken that handle a little bit. Right? I can definitely take the thicker handle and squish it all together. So now I've thickened the handle. And now if I kind of slide these pieces around, I'll see that it looks like a shape like this, which is a cylinder. So I now have a cylinder because I've passed Q. Let's keep going. We're going to go until we have a chocolate dip. You were responsible for bringing your own chocolate to dip. I'm just bringing the donuts. When A is a little bit bigger than R, MA will look like M when it's a little bit less than R plus a 1 cell. And again, so this is something like a cylinder plus an open interval. I don't quite have a name for this shape. I guess it's kind of like a donut with a bite taken out of it, but I'm going to draw you a picture. So I start with my cylinder, and I'm adding to it a 1 cell, this line. I can play the same kind of game as I can have my cylinder, and I can just fatten up that line a little bit. And now if I just spread it along the edges, what I end up with is a shape like this, a donut with the top cut off. And to just take it home so that we're all happy and we can say that I made you a donut, what happens when I pass the uppermost critical point? MA will look like it when I'm just beneath that critical point, the 2 cell. So again, as I don't have a word for this weird shape, what I am doing is I'm taking this donut with the top cut off, and I'm going to attach to it this 2 cell in a way that caps it all off. And so what I have done for you is made from the information of critical points and their index a Timbit, that is to say a sphere, and a slightly more canonical donut, one of the larger, fancier donuts, in particular a torus. I hope that was not like way too aggressively fast. I hope that the desync between what me writing and what you're seeing on the screen was not too large. And I just hope that everyone had a fun time. That is all I have.
All right. Well, I'm going to simulate the applause since I'm the only one in your distinct vicinity. Okay.
The crowd is going wild, people.
Yeah,
it's crazy.
I can feel the enthusiasm for everyone. We're gonna maybe stick around for a minute or two, wait for anyone who wants to join the question queue, get a comment in for Christopher before we wrap up. But yeah, this is a great way to start off. I'm definitely not experiencing anything remotely close to this. I'm a statistics major, so but I was still. We have claps from Robert, and then we have other people in the chat.
Thank you. Yeah. Thank you.
So, if there's no questions, if there's no one joining the question queue immediately, I think we have a question from...
Oh, I'm just being trolled by people that I invited to the talk.
Okay. If there's no one immediately joining the queue, I think I need to just do some MS Cube things. So next week, there's not going to be Math Talk. There's going to be actually a different type of event for us. There's a Dr. Stephen Ryan, the graduate chair at U of S, is going to give a quick session about applying for graduate school. So if you're a math or stats related student thinking about applying for graduate school this fall, consider coming. It's going to be next Wednesday at 5:30. Join our email list or keep in touch with our Facebook page or our Discord, and we will circulate the information on that. I believe that's going to be on Zoom. So thank you again. I'm going to clap again as it's customary after the question period. Thank you, Christopher, for joining us for our first Math Talk. I think it went smoothly. I know I won't know until I actually watch this all over again and see how it goes. But I think since everyone's been here this whole time, hopefully, I think it went well. So thank you, everyone. And I'm going to say goodbye unless, Christopher, if you have any closing comments for the...
No, it just, thank you for having me. I'm very happy to have given the first talk. If it was well enjoyed and you need another speaker in the future, I can definitely come up with other fun titles for talks that are actually about mathematics.
Awesome. Yeah. If there's by chance anyone watching this who's a U of S undergraduate or graduate or like somewhere in the department, hit us up at our email on our website or on our Facebook page if you're interested in giving a talk like this. That'd be great to have a lot of diverse math and stat voices talk about math for us this year. I think Robert's next up next month, but yeah. Okay, so I'm going to end the stream now. Thank you, everyone, for joining us. Thank you, Christopher.
Thank you very much for coming.
And yeah.